Hello, everyone, and welcome back to Andy's BrainCast. Today, we are joined by Dr. Alfonso Nieto-Castañón, who is the director of the Computational Neuroscience Research Lab in Santiago de Compostela, Spain. He was previously a research affiliate at the McGovern Institute for Brain Research at the Massachusetts Institute of Technology, where he developed the CONN Toolbox, the most widely used functional connectivity analysis software package in the field. I feel pretty confident saying that. If it's inaccurate, that's all on me, but just the citations, it does seem to be true. He has won several computing programming competitions, including the Microsoft and Chaleurn, I think I'm saying that right, Chaleurn Data Analysis Competition, and the Genentech Data Prediction Competitions, along with being awarded Google's Kaggle Competition Grandmaster title. His research focuses on modeling and statistics, brain imaging methods, and machine learning, especially the understanding and characterization of human brain dynamics. So welcome, Alfonso. Thank you so much for being here.
Thank you very much for having me. That was an incredibly nice introduction. Thank you very much, Andrew.
Of course. And also, well, from my perspective, very impressive. I'm not a professional programmer by any means. And I actually want to start there because this is one of the reasons why the CONN Toolbox exists and why it's so widely used and works so well. Something I didn't include in that introduction was for, I believe, 7 consecutive years, you were also ranked first in MathWorks coding rankings among 100,000 MATLAB programmers. So this is all to say, from my perspective at least, is very impressive. How did you get to that level, maintain it, and how did that lead to your pursuit of applying those talents to cognitive neuroscience and not, say, working for Google or Meta or something like that? Why this route?
That's a great question. Thank you very much. And yeah, I mean, a lot of those competitions are kind of like the product of the youth. I was young and had a lot of time on my hands. So I participated in competitions and did all of that. Now that I'm a little bit older, I'm a little bit more focused on my research, but I still can enjoy the
regardless
of all of those accomplishments. And yeah, I mean, my background really is in electronic engineering. I studied back in Spain, and I was got interested into the whole neural networks framework from an engineering perspective, and that was kind of like my lean into the brain and figuring out just how that works. But it was mostly from a practical perspective. I was thinking as an engineer, how can we mimic that behavior? How can we? And then only later on, when I did my PhD and all of that, I got interested in how it actually works, and how we can fix issues when it doesn't work, and what can we learn about it? And because it was one of those, to me, like amazingly complex and interesting questions and I'm a very competition driven. I'm pushed towards the difficult stuff. And so I don't know, it was one of the things that attracted me the most about the brain was how challenging of a question. And I didn't think I would be able to understand how it worked in a lifetime, but I thought it was a nice pursuit to try. And so, with my PhD, I studied in CNS and Cognitive and Neural Systems Department at Boston University back in the day. It was like a big place for neural networks and all of the big ideas in how the brain works and how to simulate that. And were being developed, well, a lot of them were being developed there by, Grosvenor and all of these people. So I got interested then in neuroimaging as the tool to learn about the brain, and it was a very novel tool at the time. I remember that back in the day when I was studying, I started developing some methods to analyze statistically the data, and we were addressing issues that were very, very basic, or at least today they are considered very, very basic, which is how do you correct for the correct degrees of freedom of the data so that you get nice statistics out of it that are meaningful. They are not all p-values that are ridiculously low.
Right.
Slowly I got into the method development in neuroimaging, and it was a very interesting field for me. And I was working on things like ROI, regions of interest, trying to define regions of interest that were localized to different people, to try to find the association between anatomy and function, those type of issues. and at that point is when I started getting interested in functional connectivity, which was also a very novel thing by that time. And the lead into the CONN Toolbox actually started from this collaboration with Susan Whitfeld-Gabrieli, which was working at MIT at that time. And she was already working on functional connectivity and had some ideas about anti-correlations between the full mode network and, well, some areas basically, and in that between the dorsolateral prefrontal cortex and, anterior medial prefrontal areas. And she was interested in she thought that these anti-correlations were meaningful, and it was interested in developing them further and studying them. But there was a technical glitch at the time, which was that anti-correlations were very much frowned upon in the field. People tend to think that, right? If something was an anti-correlation, that it was probably wrong, like just focus on the positive correlations because those are the most meaningful, when Visual was talking about the correlations, all of those seminal papers, they were all looking at positive correlations, and it made sense to think of the brain, in terms of correlated areas that I'm kind of like doing the same thing, joining on the same mental processes and things like that. But it was strange to think of anti-correlations at that time, and people thought that it was perhaps an artifact of the of the method. And there was also this paper. It came a little bit later, but it was this paper by Murphy, and I think it was 2009, something like that.
Yeah, Kevin Murphy.
Yeah, remember that it was talking about how when you use global signal regression, a technique that it was used at that time to correct for the data, then, the anti-correlations will pop up from the data, even if they didn't exist. And that made people nervous, and they said, well, let's just focus on the positive correlations and forget about anti-correlations. And Susan didn't want to do that, and asked me basically how, because I wasn't kind of the methods person in that environment. And she asked me, well, how can we actually deal with those anti-correlations in a way that is meaningful, that we can actually talk about them and find interesting information? And and that was kind of like my lead into the functional connectivity. I started thinking about how we could, develop that correction. Actually, I didn't develop that. That was a method. I used a method that was developed by the SARI, the Anatomical Concord. It was a very novel method at the time, and they just came up with this idea. It was for task-based analysis, but it was the same idea. Why don't we look at white matter and CSF areas and try to define noise by looking at what happens in those areas where we know that there are no neural processes going on, And I thought that was a great idea, and it would actually address exactly what we needed, which was a way to correct for noise sources in fMRI without including the signal from gray matter areas, which was the problem with global signal regression at that time. So without making the story too long, that was kind of like my lead into how I got started. It's a very long story, but that's how I got interested into this in this field.
Well, that's very interesting. I mean, the history of all this is always useful because we need to know where these things came from, why we use certain techniques and not others, what some of the debates were. And just to give a little perspective, so that original Visual paper, that was 1995, I believe, and then there's that famous Fox et al. Anti-correlations paper in 2005, give or take. And you mentioned the Murphy paper in 2009 about global signal regression, how it could possibly, I think mathematically it will introduce anti-correlations, which is why a lot of people were starting to get really suspicious. So
it forces the mean to be slightly negative, and because the mean is negative for the distribution, then about half of the data is going to be negative. So it forces those anti-correlations to show up. And it's a very nice thing to look in the data. When you use that method, you actually see those anti-correlations going to be stronger than what you're used to. That's kind of the thing.
But it is interesting when I use something like the CONN Toolbox, for example, and I use this AnatCompCore technique to filter out noise components from CSF and white matter, that distribution still does, for most of the subjects that I analyze, it does tend to become normal around 0. There do tend to be a roughly equal amount of negative positive correlations, pretty similar to what you'd see in global signal regression, just you're not mathematically predetermined that you're going to have these negative correlations. Is that correct?
That is a fantastic point. You make a very good point on that. And when you actually correct without mandating it by the method, without including portions of the signal that come from gray matter, and basically they force that anti-correlation, that average correlation to be 0, you still see relatively centered distributions. But if you look at the detail, they are not exactly the same, because if you look at the distribution of global of connectivity across the whole brain, like every voxel to every voxel in the brain, and just build a huge histogram of the connectivity, you notice something that looks normal, but it has a long tail, and that makes a positive tail, and that makes sense because you have local correlations which are very strong, and you have like interhemispheric correlations which are also unusually strong. So local connectivity and interhemispheric correlations all are unusually strong. So they in the display of the correlation structure of connectivity, you see these long positive tails. And because the distribution is skewed towards positive values, then the mean is actually slightly towards the right? So when you actually center it by using GSR, for example, the global signal regression to center the distribution, what you get is that the mean is actually 0. But if you look at the peak of the distribution, it's slightly negative, actually. The point, the mode of the distribution, the point where you see like the maximal amount of connectivity values is negative because the average is, because of the skewness of the distribution, is towards the right. So forcing the average to be 0 forces the peak of the distribution, the mode of the distribution, to be negative. And that is a sign of something being strange, that it shouldn't be like that. And that is a difference also. One is subtle, but it's a very clear difference when you look at the details between the method that like anatomical concordant performs this correction without mandating, forcing the average to be 0, and a simpler but a little bit more rough method like global signal regression that actually forces the average of the connectivity values to be 0. So we are actually working on, we can talk about that later if you want, about quality control measures. And one of the quality control measures that we have in CONN actually looks at this, actually the position of the peak of the distribution. And that is one measure that actually can help you discern the pros and cons of different methods in the context of denoising for functional connectivity analysis. So.
Well, before we leave off of that topic, for someone who is new to functional connectivity, what was the rationale for using global signal regression in the first place? Because it was pretty widespread. Then there were some doubts about whether it was appropriate. And there was some rationale about how it could correct for certain physiological noise. What was the rationale, and is it still widely used or not from your perspective?
Right. So it made perfect sense. There was nothing wrong with the idea of global signal regression as a first approach. The first time that if you start from scratch and you just look at the ball signal and you are used to doing task activation analysis, right, where you just look at whether the activation changes as a function of your experimental paradigm, then look at the ball signal, that same ball signal with an experimental paradigm, because you acquire the data using a resting state paradigm, which is supposed to be the person doing nothing, even if that doesn't quite make sense, But you look at that data, just compute the raw correlations. Let's say that you just compute correlation values across every voxel of the brain. What you get is a distribution that looks very different for every subject, and all of them show different amount of biases. It's like the distribution is not centered, it's positive, but sometimes you get a subject that shows like a huge shift towards the positive values, and it looks like everything is connected to everything in the brain. So that doesn't seem true or correct. And some other subjects show also some amount of biases, but they are not so extreme. And that changes a lot between subjects and between sessions. If you do it one time and then you repeat the same subject in a second time in a test-retest kind of like a framework, you also get different shifts. So it was obvious that there was some global aspect of the ball signal that was influencing the correlations, and then it was inflating these correlations by a variable amount for every subject. And people didn't know at the time what that was about, but it was obvious their effect. The effect was that distribution was shifted towards the right. So a very reasonable approach is, well, why don't we just center the data? Well, why don't we just remove what is happening on average across the whole brain and just look at the difference in correlations between voxels, disregarding whether the whole brain appears to be connected to everything by everything to everything, or not. The logic of it theoretically also makes sense if you have like things like artifactual influences on the ball signal, like respiratory effects or subject motion effects. Those tend to be global in nature. They tend to affect a lot of voxels. So when you look at the correlations on the ball signal, if they are all affected by the same noise, they tend to show a high correlation. And that was the rationale for trying to remove or decrease those effects on the correlations or on the connectivity that appear by global sources of noise in the ball signal. So it made all perfect sense until we start to look a little bit in finer detail, and then we thought, well, perhaps global signal regression is not great, because when computing the global signal and the average ball signal across the brain, we are mixing a lot of things. We are of course, considering all of the noise influences kind of like together on average, but we are also mixing true neural effects because we are getting the signal from gray matter voxels that contain a mixture between noise and actual true signal. So perhaps we shouldn't regress that thing. Perhaps we should regress something else. And that's how all of the denoising framework started. And I think it's still used a lot in global signal regression in a sense because it's a very simple measure. Just do this procedure and you get a very drastic improvement of the data. It's like a quick and dirty approach. If you are not going to do anything at all to the data, at least do global signal regression because at least you get rid of these huge effects because otherwise the functional connectivity values are not going to be easily interpretable. But then, the field has progressed and we can do better basically than global signal regression. And that's what even those, oftentimes you see papers that actually use global signal regression. And there are people that are arguing that global signal regression actually improves reliability and many approaches. So it's a very contested debate still. In my opinion, at least, I think global signal regression is a great method as a first approach, but as you get, we now have better approaches that do not explicitly use the global signal regression, regress it from different areas like anatomical concord, and you use a multidimensional representation of noise as opposed to just a single univariate average representation of noise. So I think there are better approaches that do that work that global signal regression does even better. Even though, it's a very hot topic in the field still these days.
Of course, it makes sense to me, the approach that you've taken for the reasons that we've stated already. But one thing about Anatomical core, just for my own curiosity, I'm sure for a lot of people as well, I don't think anybody would have any issue with regressing out some kind of profile taken from cerebrospinal fluid. We know that there's no brain activity there. That's fine. From the white matter, I've heard murmurings. I haven't looked at this too much, but some people say, why are we completely disregarding this really large part of the brain that has heavily myelinated neurons and assuming that that's noise and only focusing on this thin, relatively thinner layer of the gray matter? So I've never really questioned it, but since you're here, if you have some insight into that, can you talk more about why we use an Anatomical core on both cerebrospinal fluid and white matter?
Right. So first, we keep it separate. We use anatomical core on both regions separately in a way to give users the flexibility to use one, the other, or both. So there are other approaches to anatomical core where just use a global mask and then you do principal component on that and then use those regressors. We keep them separate mainly because of these issues that you are raising. They are not equally. The rationale for using one or the other, they are not equal. And the field, even though there is not consensus yet, I've looked a little bit at the literature that is looking at, effects in white matter, and they are even building, independent component analysis of networks within white matter just from the ball signal itself. This is still not 100%. This is a developing field, and I'm paying attention to it because I'm also very much interested in exactly your point to what degree the information within white matter is actually relevant. I still haven't seen convincing, physiological arguments of how the ball signal in the white matter tracts, in the axons basically comes to be. What is it that it actually produces those neurally, as fluctuations in the ball signal that are related to the amount of activation that is, or the information that is transmitted through those axons. But so this is still contested, but you are totally right that in the future, if this happens to be the case and we get to actually see some correlates or clear correlates of function in white matter areas, then it would make sense to kind of de-weight or even disregard completely the white matter section and focus on CSF alone. There is also different approaches that have been proposed that are similar to this. There is an approach that focuses on just the ring outside of the brain rather than focusing on the ventricles, CSF. Just look at what is happening outside of the brain. But there is build kind of like a ring outside of the brain and get the signal there and then do the rest, basically, either the average or principal component analysis over those areas. So there is still a lot of research going on in precisely how to best define anatomically the regions that will give us the best characterization of something that is as clean as possible, characterization of noise, and as uncontaminated, so to speak, by gray matter activation or by true neurally based fluctuations in the ball signal. So
yeah, again, I realize that there's pardon the pun, a gray area here about what exactly should be used. And I'm glad to know that you're open and flexible to new developments. But you also can't argue with the results. I mean, Anat-Comp Core, again, my experience from all the papers that have been published, it works really well. It makes it much cleaner. The results look reasonable, and in the absence of anything that is clearly superior, unequivocally better, logically, results wise, I think we can be comfortable continuing to use it.
Definitely.
Yeah.
Yeah, I mean, in that context, another kind of competing or kind of like simultaneous approach that is also very popular and very widely used, and I think is also a very good approach, is fixed ICA. Like using independent component analysis to establish kind of like a breakdown of all of the activation across the brain into independent components, and then use some sort of machine learning algorithm to figure out which components are noise and which components are signal, and then those noise components are the ones that we regress out, similar to what we do in Anatomical Core. That's another competing approach that has been used, and it's also very popular. In my mind, kind of like that, it's a sideline operation, because the machine learning operation that tries to identify whether a component looks like noise or looks like signal, it often weights a lot where that component is located. Basically, if it finds it outside of the brain, or it finds it in white matter or CSF, then it's likely noise. And if it finds it in mostly gray matter areas, then it's likely a true signal. So it's a little bit of a roundabout way, and I think Anatomical Core does a better job, in my mind at least, to set those as a priori conditions for noise components, to define that they must be defined from signal that is purely within these areas that we know, or be pretty certain that nothing interesting is happening, just noise, versus letting ICA get components which are going to be a mixture, even if they are still mathematically independent and all of that. They are still going to be a mixture of different things, and then try to identify them. But again, this is an open and very contested topic, and there is a lot of development in this field. So I just want to mention that beyond global signal regression, which is at least in my opinion, phased out a little bit, there are other competing approaches to anatomical comport that are also very good, and they are kind of like more on the same grounds, of equally balanced and equally useful in the context of denoising the ball signal. So.
Of course. I know we've been talking a lot about technical details so far, and this is all important. I was just thinking as we're talking about all this, obviously this is an interview that assumes that most people already know some of the basics of functional connectivity, but to take a step back for people who may not be as familiar, not that we need to recap the definition of functional connectivity in detail and the history and everything, but I want to point out before I forget that you and Susan Whitfield-Gabrielli and some other lecturers host this CONN Toolbox, let's say, training camp, both virtually. Is it still in person also?
Yeah, we try to do it, but we haven't done it in a couple of years. But we try to do it every year or every 2 years, at least in person. We will see how that continues. But we do it definitely every year online.
Okay, yeah. So for people who are interested, if they're graduate student, postdoc, faculty member who uses functional connectivity, I just want to give you some time to promote it and talk about what people would learn, because I had the opportunity recently to attend it. I thought it was great. It was exhaustive, and sometimes exhausting because it is a lot of information, but extremely useful. So if you want us to say a few words about what it is, what you'll cover, who should apply, what can people expect, the floor is yours.
Thank you very much for the opportunity. Right. I mean, the CONN Workshop, we call it, is a course that is very, as you said, very involved. It's 10 classes, 3.5 hours each. So it's like 35 hours of content. And we distribute it over either 5 weeks or 10 weeks. So it's a very slow, to give people time or attendance time to practice and to get to, practice stuff. We have homework and we have office hours to help you. And, and it's open to everybody. It has a very wide net of people that I think the course may be useful to. We have sometimes, a lot of graduate students that come here to learn about functional connectivity in general. We talk about all of that, functional connectivity methods and all of the important places or important things to know when you're running functional connectivity analysis, and how to do it also in CONN, of course. So that is useful as a first approach. But we also have a lot of people that come from a more experienced background, and they are like postdocs that they have their own research questions, and they are using perhaps the CONN Toolbox, and they just want to know more about one specific method or two. And then, this is kind of like the ultimate source of information for CONN. You just come to the course and ask whatever questions you have, and we will answer them. And some people even bring their own data, and we help them go through their data and see what issues they might run to. And then, last but not least, there are also like researchers, and that perhaps are using the CONN Toolbox or are using connectivity, or perhaps they are not, and they just want to see what is out there and basically think about what else can I do with my data? Are there other questions that perhaps I have not asked my data, other methods that I haven't used that may be useful to answer my research questions that I have for my grants? Those type of people also, I think, benefit a lot from coming and hearing these very long and exhaustive descriptions about everything that is possible to do with functional connectivity. So yeah, in that sense, I will welcome everybody from novice to experienced users, and thank you very much for giving me the chance to talk about this. So yeah, this is a course. We actually, from a disclaimer perspective, we use this as a funding source for a lot of the work that we do for CONN. So if you just like CONN and you want to, help us continue doing that work and just learn something in the process, coming to the course and getting our certificate and learning a little bit about what is the things that we have been doing is a great way to help as well. So
absolutely. Again, I had a great experience. Obviously, I've been using CONN for a while before that, but still, there's a lot. It always helps to cover the basics. Again, basics doesn't always mean easy. It means it's basic. It means it's fundamental, and you should really have a good grasp of that before you go on to do more advanced techniques. So we'll put a link to that down below. I just wanted to let people know about it because, again, there's no better way to learn about it than straight from the source.
Thank you very much. Yeah, you're totally right. I get carried by the techniques and the details, and I perhaps kind of like, forget or don't mention the bigger picture. So these type of courses that allow you to have kind of like the bigger pictures are a great source. I would like to say also that your resources, you have fantastic resources and educational materials out there. And I think they are absolutely great. A lot of people actually come to the courses and they tell me that they already went through all of your videos and they have seen
that's great.
And it's a great resource for people that are starting out. You have made a great job at putting together kind of like all of the basic information, and I really appreciate that as well. So I don't know, it's a great thing coming from you that you like my course, because I think your content is always the best.
Thank you. No, my pleasure. We're all trying to make this as accessible to as wide an audience as possible, right? The more people who can use it well, it's a mutually beneficial arrangement. Right.
Yeah.
So yeah, I think we're all trying to help each other out and in agreement there. So to maybe dive back into the details now, because again, this is what I find most interesting. And I think since we have the opportunity to talk to you, this is what a lot of people would benefit from. We're talking about preprocessing and denoising, which are, again, pretty broad topics, but in general, for preprocessing, I think a lot of people are pretty comfortable with how they preprocess functional data. For functional connectivity analysis, it's not too different from how you would process task-based data. Maybe there's some different thresholds because functional connectivity is more sensitive to motion physiology. But also, when we get into denoising, I just want to get your opinions on some of the latest recommendations that people might need to be aware of. There's a recent paper you published with Morfini. If you want to talk more about that, just what's the consensus or the general view from your side of things about preprocessing and denoising these days?
It's a great question. Thank you very much. So yeah, denoising is a interesting topic itself, because at least from my perspective, because as you know, as you mentioned, there are a lot of people that come from task-based activation analysis, and they are already used to preprocessing the data. That's all fine.
Mm-hmm.
And after preprocessing the data, they typically jump to first-level analysis. They will take, FSL or SPM and run their models with that data. They don't even think about denoising the data. What does that even mean? It's something specific that arose or kind of came to be in the context of functional connectivity, mostly because of what we were discussing before, that idea that those sources of noise in the ball signal in the context of functional connectivity, they tend to produce inflation of the correlations, and they look very weird and they were very salient. Those same things existed before. They are in the data, in the ball signal. It's only that they don't affect task activation analysis at all. Well, it's not at all, really. They only affect kind of reliability. They affect the precision of the measures that you get. But because single subject reliability is not terribly important for second level analysis, then people just deal with it. Say, well, my first level measures of task activation are noisy. I have 100 subjects. What do I care? I don't need them to be very clean. And they don't think about denoising. In the context of functional connectivity, denoising, it was a big issue. You couldn't just forget about it because it was biasing your functional connectivity measures. You could see them. They are all of them biased towards positive values. You can pretend that they don't exist, those biases. So that's why denoising became a thing. And there have been a big development in the methods that have been used in the context of denoising, as we mentioned before, kind of like in the context of global signal regression, anatomical core. Scrubbing was also one of those big things that happened. There was this paper by Power and others in I think it was 2009, perhaps, or a little bit later. I don't remember, talk about how motion was a big thing in functional connectivity. And particularly in the context, they even came to talk about developmental trajectories in children, how the different amounts of motion that you have in children, depending on the age, was one of the driving factors in difference in functional connectivity that you actually studied and published in many papers. So it was a big paper that came kind of like a notice that motion was a very problematic thing, and we should take care of it very, very conservatively. We need to be more aggressive about dealing with motion, at least when doing functional connectivity analysis. And in addition to methods like anatomical core and fixed ICA that came to prominence, the use of a method called scrubbing, which is basically identifying the places where the subject moved a lot, effectively kind of like remove them from the data. It's not exactly remove them. It's a little bit of in the field confusion about what is called censoring, which actually removes some data points from the time series, versus the scrubbing, which just models what is happening in those time points. But in any case, it was the need to deal with those specific time points in a very aggressive manner and make sure that the measures that we compute on functional connectivity, for example, they were not affected by whatever was happening at those points where the subject moved a lot. And that is a method that is called scrubbing. And it's also one of the main components of a good denoising pipeline. You need something like anatomical core or fixed ICA to remove physiological noise sources. You need something like scrubbing or equivalent to remove the places where the subject moves a lot. And then we also need things that are also common in the literature of task activation. We regress out anything that correlates with how the subject moved, motion parameters and things like that. Those are kind of like the last segment of the components that we are typically combined into a good denoising strategy. As you mentioned, the paper with Morfini, it was part of a Frontiers special issue about quality control. And lately, or at least I'm particularly interested in the context of denoising, is about quality control. I want to make sure that the choices that people and myself make when selecting one or another algorithm are based on the data, basically whatever works better for your data, rather than having to trust one method or the other when you don't have a clear basis to choose one over the other. So having ways to quantify actually the effect of one procedure, one denoising procedure versus another, I think is very, very important for the field, basically, to come up. And so we had this special issue where many different people came and talk about what their quality control procedures were using different software packages. We have like Paul Taylor from from
AFNI.
From AFNI, sorry. And we also have as well, Oscar Esteban, FMRI Prep. We have a lot of different people coming from different software packages, and all of them kind of like sharing what was their way of dealing with quality control and estimating the quality of your data and helping you decide which procedure was best to get your data before starting actually the analysis. And in that context, I've been actually doing a lot of work in the GUI itself, in the CONN GUI, to try to bring about these procedures and kind of like standardize it. The last version that I just published a few days ago, actually, I have incorporated a few quality control measures into the main GUI. So now in the same GUI where you do denoising in CONN, where you can just plan what is going to be your denoising strategy, by default, it's just the recommended strategy, but you can play with the parameters in there. Now you have a few measures in there that will tell you the results of the denoising in numbers, and you get linked. The goal is basically to get those numbers as high as possible. You have like a percentage number of data quality, data validity, and data sensitivity that measures three aspects of the quality of your data. And the idea is that people will improve or try to change their denoising strategy to maximize those numbers, because as there are different cultures in the context of quality control. My perspective is that we need to build methods that are specific to each data set. It's not rather than trying to impose a convention for saying, we should always remove motion above 0.2 millimeters. I think those conventions are not helpful, because in many cases there is no, a practical use of that. You just have children, and you cannot remove that because you would end up with no data at all, for example. So rather than using those abstract conventions, I think that it's best when you define quality of your data in a data set specific manner. So rather than removing all of the subjects that moved, above a threshold, remove the subjects that move more than everybody else in your sample, right? The ones that are outliers with respect of motion, for example, so that you get a data that is relatively homogeneous, is representative of what is happening on that sample that you are actually driving. It has perhaps some level of contamination of noise, but at least you can analyze it, right? And so data set specific conventions, I think, help the field move forward. They're more realistic. So I'm, building all of these tools to try to give users and researchers measures so that they can quantify the results of their denoising procedure, and then compare different approaches. If you want to try global signal regression, then by all means, go try it out and see how it works. If you want to try fixed SCA on your data, go, try it out and see how it works, and then base your decision on how well it worked on your own data. So that's kind of the general perspective of the quality control, improvements and changes that we have been adding to the toolbox without getting into too much details.
Yeah. Okay. That's great. That's just a few days ago you made this release.
Yep.
Well, I need to give that a try. Excellent.
This is a pre-release. We have two versions of CONN always. We have the yearly release, where it's the stable release of CONN. Every year we have a new version, and then you have the early access release that we have that in GitHub, and you can download pretty much the same thing that we are working on these days. And this is where we release this version. You can download it, give it a try, and give us feedback, because that's why we do these pre-releases. If people tell us, well, I don't find this measure useful, why don't you do this thing, or why don't you, they give us suggestions, they give us feedback. I think it's this interaction with researchers that actually use our tools is one of the main things that we use to drive development and to make sure that our tools are useful and they are, easily, people understand what they are doing and people have the means to do what they wanted. So,
right.
Try it. Let me know.
Okay. Yeah, I will. I want to go back to something you said about analyzing populations such as children. And I have a confession, maybe not that much of a confession, but one of the questions I get asked that is really tough for me, like I prefer not to get asked this question, is I'm analyzing a sample for children, older subjects, people who move a lot, and I have to remove a ton of data unless I make my thresholds a lot more liberal. For example, I'm not eliminating any volumes 0.2 millimeters. I have to bump it up to 0.5, 0.6, so that I have at least 70, 80% of my data. And I usually just don't know what to say to that, because I feel that if I do, for lack of a better word, placate them and say, oh yeah, that's fine. They might just be analyzing a very motion contaminated data set. And if I say no, I'm going to break their hearts, and they can't analyze this data set that they've spent a lot of time. It's a special population, somebody with schizophrenia or ADD. Not to put you on the spot, there may not be a good answer, right? What would you say in that situation? Somebody who has a really messy data set, and they come to you hat in hand, they're really upset. They want some good news from you. What would you tell them?
That's a fantastic question, and that does happen. I see that I get those questions as well. Let me see how to phrase this. First, let me start by not being in total agreement with absolute thresholds or the utility of absolute thresholds. Let's say that if you have like a 2.2 millimeter motion, that is a convention basically for an absolute threshold, and it's a very common one, is to remove anything that is above that threshold in average motion, or even remove individual scans that are above that threshold. Removing individual scans that are above a fixed threshold makes sense, but removing an entire data because the average motion was that level, it's an absolutely, well, it's not absolutely, but it's very much relatively meaningless measure. When you measure 0.2 in frame-wise displacement, for example, what you're actually measuring is the change in position of the head between one scan and the next. But that doesn't take into account at all the time it took to change between one scan and the next. If you have a fast acquisition, that 0.2 millimeter motion is much faster than if you have a slow acquisition. The 0.2 millimeter motion could be, if you have a very slow or a sparse design where you are sampling every 10 seconds, 0.2 millimeters is a very conservative, extremely conservative threshold. So first, just to note or come to the realization that setting an absolute threshold doesn't always make total sense on the data. And then the reality is that the more motion that you have, and particularly the stream motion cases that you have, tend to have effects in the ball signal that are very, very difficult to process. That is what is happening, and that is what is driving all of these problems. We can measure very well how the subject was moving, but we cannot correct for it meaningfully. We can correct for rough, rigid body transformations, but that doesn't correct for interslice differences in motion, kind of like within acquisition motion. We have even better methods that correct for inter-time acquisition, scan motion, but they don't correct for spin history effects. There are a lot of complexities in the effect that motion has on the ball signal that make it all of these linearity assumptions of all of the methods that try to correct for motion fail after a point. So the reality of it is that after motion becomes too much, whether that too much is difficult to describe precisely, then you have effects in the ball signal that are very difficult to correct for, and that you are better off just disregarding if possible. And that is where the scrubbing method comes to be. When you scrub out places where the person moved a lot, you are basically removing that influence of the potentially difficult aspects of the ball signal changes that you cannot correct for effectively, and you are just trying to keep kind of like the clean portion of the data. And the last thing before coming into the actual recommendation, the last thing to comment about sorry, skip on mine. I was going to say. Sorry, I forgot. So let me go back into how to use them. The actual recommendation that I do to people that are in that situation is that they can analyze the data perfectly fine using these kind of like data set specific conventions. Just remove the subjects. If you need to remove subjects, remove the subject that move the most. But then keep an eye on the subject that have moved more than usual. Oh, I remember now what I was going to say. Another thing about absolute conventions in thresholds is that they are unrepresentative. If you have a disease that has a motion correlated, if you are looking at, or if you are just looking at elder population or younger population where motion is a part of being that, by removing subjects that have very low motion, you are not being true to the data. You are not analyzing the normal subjects. You are not analyzing the subjects, the subset of subjects that move the least. And that creates very complicated relationships with the disease or with age or with other factors that are related to the amount of motion that are going to be getting into your analysis. When you show a result that is not going to be about that population, it's going to be about the subset of population that didn't move, or that moved the least, kind of like within that population. So all of those approaches, even if they look kind of like the safest approach, they are not all that safe to begin with. So that was kind of like the main point. And what I recommend is to actually analyze your data. Still remove the subject that move most than anybody else within that sample. Those are that are outliers. But then analyze your data, find your results, and then be very careful in the interpretation. Know that because you are analyzing data that contains motion, and motion is a big thing in functional connectivity, there may be some correlates with motion. And then do your best work to try to convince yourself and the reviewer and the readers of your papers that the effects that you are finding are not, or perhaps they are, being modulated by this. So how can you do that? You can actually regress out motion, for example, in your second level analysis. If you find, difference between groups and you think that one of the groups may be actually affected by larger motion, well, use an ANCOVA analysis and control for motion between groups. If you think that you find a result within a group and you are concerned that perhaps it's introduced by motion, well, then analyze the subset of subjects that move the least and see if your results replicate. There are a lot of techniques, kind of like post-hoc techniques a posteriori, that you can do on your own analysis to convince yourself whether the results that you're finding are biased or are introduced by motion or whether they are not. So if you do a good job at that, I think that is the best of both worlds. You get to analyze your data, but then be very careful and try to spend a lot of time convincing yourself and learning whether the results that you found are actually influenced by motion or not, to the degree that you can with the data that you have available.
Okay. Well, I'm glad to hear that. I think that's a good recommendation. It makes sense to me. If somebody's using something like FIRMM, I don't know if you've used that. What are your thoughts on that? Because first of all, I think it's an excellent software. Basically, in real time, as you're scanning, let's say you want 10 minutes, it keeps scanning until you get 10 minutes. It flags if there are any motion above a certain threshold and keeps scanning, so you have a good data set. But it always seemed to me that you might be running to the same issue where you may be removing data that's representative of a certain population. They do tend to move a little bit more. And also, if you have to scan half an hour to get 10 minutes of data, what does that say about that subject compared to somebody who you don't need to remove anything? So what are your thoughts on FIRMM? Have you used it? What are your recommendations on that, if any?
Right. I haven't used it myself. I know the method, and I think you are spot on your thoughts there on the pros and cons of something like this. But I'll elaborate a little bit. But I think you got the right idea exactly. So the advantage is basically that you can get a lot of sufficient kind of like clean data even from bad data sets. I've seen this used. I haven't used it myself, but I've seen it used kind of like in fetal analysis where there's huge motion and you need to kind of get the glimpses of motion when the fetus is stable, and then get that and use that for your analysis and do that. You have to scan 2 hours to get 2 minutes of data. But so this is not such a extreme case, but it's kind of like the same idea as you just scan longer and try to find kind of like sufficient time points to analyze your data. I mean, the idea is great and the practice is actually great as well. And it also addresses one of the important issues and concerns that people have about describing. When you remove individual time points that have a lot of motion, people are concerned. One of the concerns about that approach is that perhaps we end up with different reliability, a different precision of individual subject measures, depending on how much data we remove. Perhaps the subject that we removed a lot of data, we are going to get not so clean data for functional connectivity because we have less data to work with, right? So our functional connectivity measures are a little bit more noisier than for subjects where they didn't move as much and we have more data points. So that creates this heteroscedasticity problem in second level analysis where the precision of the measures that you get across subjects vary, and you have some subjects that you have high precision of measures and other subjects that have very low precise functional connectivity measures, and that affects the validity of the second level analysis. So that is a concern. This approach works perfectly for that, because it forces your data to be more homogeneous across in terms of the number of effective data points that you have for every individual subject. All of them have roughly the same number of good points, even if at the beginning they have different lengths of data. So from that perspective, purely like a statistical, is a great approach. But you're also totally right that there are concerns with this approach, and one of them is that even though the number of samples that you get and the statistical reliability of your data is going to be very similar across subjects, effectively you are actually scanning different durations, and durations affect reliability in a very roundabout way.
Yeah.
One thing in functional connectivity is that the measure that we are actually measuring is not stable. It's not like the height of a person that if you do a test retest, you measure it twice, you're going to get the same thing. Functional connectivity is not even as a structural connectivity. I think that is a trait of the subject. It changes on the context. It took the field, a lot of time to come to this realization. And today we are still working on developing methods that actually truly take this into account. But functional connectivity is a measure that changes depending on what the person was doing. It's a measure that changes dynamically over time. And when you scan a person at a given moment and get a functional connectivity measure, even if you get a great precision of the measure, statistically, you get a very low standard error and you get nice confidence intervals, then you scan that person a little bit later again, and it's going to have a different value. And that is not noise. It's not actually, fluctuations in respiratory or physiological or subject motion, those things. It's just like an underlying changes in what the mental processes that the person was doing while they were being scanned, where they were their eyes open, where they were with their eyes closed, were they thinking about, the noisy environment that they're in, were they paying attention to that, or were they thinking of something else? So this is why we get these very long scanning sessions to try to measure very reliably and very stably properties of the subjects. And people are recommending half an hour or even longer scanning sessions, so that even if the person is doing very different things, over time, on average, if the scanning session is long enough, you're going to get a very good measure of what is on average doing that person and how is the brain, kind of like the functional organization of the brain behaving on average. But for that, you need longer sessions. So this procedure kind of comes very nicely into play with that idea, but kind of like in the opposite way. Now, if we are changing the duration just so that we fix the number of samples of acquisitions for every subject, the clean data, we are actually changing something that perhaps mattered most for reliability in terms of addressing the behavioral variability in functional connectivity measures across time. So perhaps for the subjects that we are scanning longer, that had more motion, we are actually getting a better measure or more representative of that subject because we scan long enough to get a representative measure of what the subject was doing. And the subjects that we scan shorter sessions because they were great and they were not moving, then we get actually a worse measure because that was an instantaneous kind of like a short measure. So it all comes down creating kind of like an additional difficulty in the effect, the practical effect that this procedure has, which one wants to take into account when considering the cons and the pros of this approach. So just repeating what you already said, but just kind of like elaborating a little bit on this approach. I think it's a great idea in general, but it needs to be taken with care because it's not all positive. There are some potential cons in using something like that to get more homogeneous data across all subjects.
Definitely. A year ago, I was talking to Stephanie Noble about this same issue because she's done work with examining reliability in functional scans. And I think her work has been instrumental in making people realize we can't always just throw in a 5-10 minute scan at the very end and expect that this is going to be enough to lead to any kind of reliable effect. It's the same mindset. I always try to argue from the perspective of that would never fly with a task-based experiment. But why aren't you giving the same respect to functional connectivity? Okay, it's easier to scan though, to do that scan because people are not really doing anything. But 5 to 10 minutes, it's becoming increasingly clear that that's not enough to lead to any kind of stable representation, let alone do any kind of dynamic connectivity analysis to see how it changes from time point to time point. But again, I understand why people don't scan that long. There are budget constraints or time constraints. There's no real easy way about it unless you're just dedicated to scanning somebody for half an hour or more to look at these differences between populations or within subjects, for example. That's just my commentary.
Sure, No, definitely. And it's a very good point. I mean, it's actually a very important point that has changed. I mean, when functional connectivity started, it took everybody as a surprise. It was like a resting state. It was so great. Everything was great about it. It was like, so you could just scan a few minutes, so you could put it into your study. And as a last thing, even a few minutes gives you a very important and, nice information. And the person was doing nothing at the time, which was also great because then, with test designs, you have all of these problems of confounders of difficulty. If you are comparing, patients and controls in a task, perhaps the task is more difficult for patients because you design that task because it's related to the underlying condition. So difficulty is a big confounder effect. Well, resting state, they are doing nothing. There is no confounding of task difficulty. It's short. You can get it in a few minutes and it's meaningful. Why don't we use it? It's only over time that we have gotten to the point where we are starting seeing the limitations of these kind of short scanning sessions, even though they are, the UK Biobank is 6 minutes and we have tens of thousands of data sets of that length. And we are definitely going to use them. We use them for that data is still useful. It's only that we have things like HCP data from the other extreme of things where we scan people for an hour. You have 4 sessions of 15 minutes, so you have an hour. Well, even more extreme, you have cases like, Raspolrak, Mike Connectome, and the Midnight Club, all of
very
those.
Very famous case, yeah.
Those are cases those are great data to work with, where you have a single subject very densely scanned across time. So I think that's in a way the future, basically where we are going towards, really. But it's a huge span of if you think about it, kind of like difference in the duration of the scanning time that we use for functional connectivity. And in practice, basically what we end up is basically a different question that we ask the data, depending on the duration of the scan. As you pointed out, basically the dynamic connectivity, if you want to actually analyze changes over time, which I also believe is one of the main drivers of in the future of what we are going to learn from the data. Those things you need really high, long durations of scanning time. And while if you just going to get like a measure and just look at brain-wide associations, kind of like in the population, then perhaps you don't need that long measure because the number of subjects is going to compensate and it's going to give you high, reliability of your correlations across subjects just by dropping more subjects in the data, even if the data of individual subjects is rather noisy and not all that clean and not all that representative. So I don't know, different perspectives, but I think it's a very, scan duration is a very hot topic as well in functional connectivity, and something that people should take into account when they are designing their experiment. If you're applying to a grant and you are thinking about how to design your experiment, think about what you want to do with that data, because that is going to tell you how much data you need. Do you need long sessions or short sessions? There is also this nice tool, the GEO tool 2000 this year. They had this paper in Nature where they but they look at I think it's in a predictive settings for predicting, brain behavioral associations and things like that. But it gives you a calculator so that you can say, well, if I scan this amount of time and I get this amount of subjects, what is the sensitivity that I get to look at a brain behavioral correlation? And they give you like a way to optimize that. And I think the recommendation is to start using kind of like half an hour at least of data to kind of like the optimal in terms of cost. But I don't know.
Yes, that web-based tool, anybody can access it. It's excellent. I've used it, and I'm glad I'm glad that a lot of these tools are available, especially web-based apps where you can use them before you even start scanning and you have a good idea what to expect. So we don't spend months or years collecting a gigantic data set and realize there was some fundamental flaw with it.
And that happens. You can be sure it happens a lot.
It does, unfortunately. I mean, we try our best to try to protect ourselves against it, but I think that Thomas Yeo's group is in the right direction, doing that kind of work. Definitely. Just a quick time check. How much more time?
I'm fine. I can go on. Don't worry.
Okay.
I don't have anything until an hour, 5:30, an hour and 15 minutes. I have plenty of time. Don't worry.
Okay. Very good. Okay. Because it's going really well, and I don't
want to
abruptly.
Sorry, I get myself kind of like talking perhaps too much. If you want, I can go for shorter responses. Don't worry about it.
That's the whole reason why you're here. Very good. So you were starting to talk about dynamic connectivity, which is, again, I'm not sure exactly how recent that technique is, but it does seem to be becoming more popular. I'm seeing it more and more. If you want, could you talk about dynamic connectivity? Maybe there's that dynamic ICA method within the CONN Toolbox, and talk about that, about how it sheds light on current ideas about state-based transitions and functional connectivity.
Thank you very much for the question. Yeah, definitely. Dynamic connectivity is my preferred topic these days, really, to be honest. It's the thing that I'm working the most, and the thing that I see holds the most promise for the field to be kind of like a radically, changing the way that we address the data, independent of the method. I think, dynamic IC, as you mentioned, the method that I developed for looking at dynamic connectivity properties is hopefully going to play a role in that. But even depending on the method, there are just the notion of dynamic changes in connectivity and the way that those changes are informative about, brain functioning. I think that is one of the, future or near future, directions in the field most important. So the idea is very simple. It's basically that, as I was saying before, originally we thought of functional connectivity as a proxy for structural connectivity. We were thinking that we were looking at a trait of, where two regions are connected, they are kind of like similarly, involved in similar tasks, or at the same time they were kind of like working together to process information. And we thought that this probably was related to, it was all of this common functionality was probably related to underlying physical connections between, projections between one region and the other. But over time, we start seeing that the two things. That first, there was not such a direct link between functional and structural connectivity. And second, that functional connectivity itself change over time. It changes over time. It's still subtle. And many people think that because it's subtle and it's not important. But I strongly disagree with that. There is this, the original paper by Federal, it said when we were in this craze of resting state data and analyzing functional connectivity from resting state data, there was these papers and this approach, which is perfectly valid, that said, even if you don't have resting state data, you can just look at your task data, regress out whatever was happening that is related to the task, and the residuals of those time series, those actually, you can analyze them as if they were resting state. You get the same thing. Just look at that. You look at the brain and you find the kind of like the same connectivity. And if you do that, you will find that it's actually very similar. If you look at connectivity during task, it's actually very similar to connectivity during rest. But I always kind of like use the same example. This is very much the same as if you look at the functional ball signal. If you are totally new to the field and you are looking at the ball signal and as an image of the ball signal, the first thing that you notice is the difference between tissue classes, right? So, CSF looks very bright, looks white, and gray matter looks, brighter, and white matter looks a little bit darker, kind of like opposite of a T1 weighted image. And if you then look at how it changes over time, you just are shown that same image over time, you will say there is nothing. The changes are very, very small. This is just the same. We are seeing the same information. This image contains the same information as the next. There is nothing in ball signal fluctuations over time, because I don't see them. They are very small compared to the difference that I see between areas. And then we wouldn't have even, used ball signal analysis at all, because if we thought that task activation differences weren't that important because they were small, but we have a lot of information gained from actually looking at those very small fluctuations across time because they were meaningful, behaviorally meaningful and functionally meaningful. So I think the same happens in functional connectivity. We have, the field kind of like starting with the idea that this is stable and thinking about changes in functional connectivity with context, during task-based analysis, and you find significant differences. You actually do find it, but they are small in effect size, so people think that they are perhaps not all that relevant. And I think the field is slowly kind of getting away from that idea and starting to think that, well, perhaps those differences are small, but they are significant, they are meaningful functionally, and they can help us understand how the brain kind of like dynamically changes. So I think kind of looking at these changes in functional connectivity over time allow us to start thinking about how the functional organization of the brain itself changes as a function of the context, right? Depending on what the person is doing, the brain is not functionally organized in exactly the same way. It's organized slightly different depending on the context of what the person is doing. And there are a lot of changes, studies in the field and methods that have been developed to actually analyze and let us look at those changes. Like there is the Allen's approach, which is basically running like a sliding window functional connectivity analysis and then running clustering. And if you try to find clusters of time points or segments of time where the person was kind of like showing the same functional connectivity, and then perhaps it changes to a different state. And there is the Vidaurre approach as well for the kind of similar, but is using a hidden Markov model, for example, an HMM model to model how changes in functional connectivity happen over time. I think the problem with all of these approaches is that they are all using what I think is a oversimplistic assumption about how these changes happen. They tend to think that these changes over time are happening as changes in the absolute state of the person, kind of like a holistic description of what the person's state was. And they are thinking, well, perhaps, now I'm thinking about the past and I'm in this current state, and then I'm thinking about something else, and then I move my brain kind of changes perhaps functionally to a different state. I think one of the big advantages of the method dynamic ICA that I'm developing is that it doesn't start from this assumption. It doesn't assume that if the brain is changing in a state-based manner. It's changing from one state to the next, and it's trying to run analysis and look at the data and see what happens if we don't make that assumption. So the basic idea is that you actually look at how functional connectivity changes. Just look at it and try to identify connections that actually change together. Perhaps it is actually the case that all of the brain kind of changes together. So all of the connections are changing, and you would find kind of one big factor that tells you that the brain is changing between these kind of different states. But what we're finding in the data is actually that is not what happens. We get clusters of connections, groups of connections that they tend to change together. But then we have a different cluster of connections that is also changing together, but it's not synchronized to this. The things that are making these connections change in functional connectivity strengths are not the same things that are driving these changes in functional connectivity in a different circuit. So we call these component circuits, and we think that actually they represent better what the brain function is. The brain is not doing just one thing. Even if we consciously are aware of just what we are doing right now as a single thing, our brain is actually doing many things at the same time. It's kind of regulating the state of the body. It's doing, it's looking at things that we are not even paying attention to, just establishing whether they are important for us to pay attention to or not. So this method actually gives us a series of circuits that actually change over time, and they are somehow independent, and they allow us to start thinking of change not as a state-driven thing, basically as changes that are happening from one state to the next, but as the combination of all of these circuits that are kind of independently changing. So I think the ability of this method to give us this kind of richer representation of changes, in functional connectivity, together with the actual, push in the field towards understanding measures that characterize those changes, is going to open really a realm of different ways of thinking about the brain and thinking about brain function and thinking about, diseases and that are not so much as a static problem in the brain, like something is wrong with the wiring, but something that is related to how the brain dynamically adapts to different contexts. So I'm a big fan of the dynamic connectivity methods, others and my own, and I think I'm putting a lot of work the next few years into trying to develop these methods and to give the researchers, the tools to actually start looking not at functional connectivity as a state property of the brain, but start analyzing how connectivity changes and whether it changes in structured ways that it will give us meaningful information about the things that we're interested in. So,
it's a fascinating field, and I'm glad you're working on it. It's the analogy that comes to mind when we think about how people's brains, how their minds operate, is if you're just looking at the state, let's say, for an analogy, there are two people leaving from the same house, going to work, and they leave at the same time, they get to work at the same time. One person is driving consistently at 30 miles per hour. The other person's driving 60 miles per hour, then they suddenly stop and they restart. And so at the very end, you may say, oh yeah, that they both got there at the same time, but their ways of getting there were radically different. You only see that if you look at these snapshots along the way. Maybe not a perfect analogy, but kind of gives you a sense of how many differences there are beneath the surface of what can look like a stable default mode network, for example.
That's a fantastic point, and I like your analogy very much. Thank you for it. It brought to mind something that is totally unrelated, but we started talking about competitions when I was younger, and there was this Netflix competition. It was a huge thing. Netflix was kind of giving their data to researchers to try to analyze, to make predictions of what the people would like, basically, depending on the movies that they've seen. And one of the problems on that data set, one of the biggest problems that kind of like drove which methods work best and not, was the mixture problem. Was that an account actually was compounded of many different people that were watching movies under the same account. And you had to tell that apart. Otherwise, you couldn't make sense of some data. A lot of entries didn't make sense because they were watching stuff that they didn't, typically come together. And I think your analogy kind of made me think of that, and that's how like a very general problem in, when you are looking at a mixture, and sometimes you don't realize that it's a mixture and how it doesn't quite make sense. So I like that.
Yeah, I started using CONN Toolbox maybe 6 years ago, something like that, and I still use it for teaching incoming graduate students, just the principles of functional connectivity, because the way it's laid out, it's very logical, very clear. Somebody doesn't need to be a coding expert to use it, because the graphical user interface is very accessible and intuitive. And then, obviously I've also been giving people options for these Jupyter notebooks with Nylearn are also very, very useful, very clean, and also not too difficult, because the Jupyter notebook interface makes it accessible to non-experts as well. So, but the main selling point from a user's perspective of the CONN Toolbox, who's not the developer, is that especially for integrating it with something like the output from fMRI prep, or downloading something from the 1000 functional connectomes project, I think those are great additions, because you don't need your own data set. You can just import something that's already been pre-processed or something that's already online. I think that's also a major advantage of using that toolbox, in my opinion.
Thank you very much. I appreciate the comment. We do, or I do, pay a lot of attention towards those aspects, of toolbox design, basically how to make them so that people can use them. They can find the data easily. They can, these days we live with these huge open databases that are available, but they are available on a technical, technically they are available, but sometimes it's difficult to get them and to understand the whole process of how to get the data, how to get something out of it. So anything that makes it easier, basically make it easier to access the data sets. I think it helps in the democratization of resources. I think in that general perspective, it doesn't make the analysis of these large data sets only the realm of very small and powerful groups and with a lot of money and resources. It makes them, analyzable, but more people, and the more people that analyze the data, I think the better for the field. So I do pay a lot of attention to those aspects, making the graphical interface intuitive, making the process by which you get from the data to the results as simple, as transparent as possible, and to remove kind of barriers of entry, so that everybody can, irrespective of their expertise or their amount of resources or money that they have in their lab, they can actually get to analyze the data. So I appreciate your comments about that as well.
Well,
thank you.
Yeah. Graphic user interfaces, again, like you said, just making it accessible to as wide a background as possible. And I think that as we, have more people entering the field with different skill sets, different backgrounds, obviously, the standards change. We assume that people have or should acquire a minimum level of coding proficiency. But there are a lot of people who, for whatever reason, are not inclined to know a lot of details about it. It's just not their field. That's fine. But they have really good ideas about some kind of experiment or something to test. And if you just through more and more people being able to use it and intuitively use it to answer certain questions, we increase the probability of some kind of breakthrough in the field. I think that's likely to happen.
Definitely. Yeah, that's a very good point. I mean, that you cannot be an expert of everything. So you cannot expect people to be, very good at their field, and also be very good at coding, and also be very good at understanding kind of like low-level preprocessing methods. And so I think, tools play a big part in that, in filling those gaps and allowing, the best ideas to come up, independent of whether you actually have the coding tools or have somebody that you can ask in your lab, because to create the analysis or create the software to run the analysis to run your ideas, basically. So I think, I don't know, from that perspective, I like to think often about the role that toolbox development and method development plays in science in general, and I think it is important also in the way that the methods are developed. There are things that are assumptions of the methods themselves that we develop that end up influencing the field and the type of questions that people can ask to their data in ways that we didn't really anticipate it when we created the method. So there are, current days there are these discussion about localization, for example. Are the methods that we are using, that cluster level statistics and all of that, perhaps biasing us to think of the brain as functionally localized, as functions being a location within the brain, or is it a consequence of the methods that we are using that it will give us kind of like these clusters, and it's not allowing us to look at effects that are kind of broader in nature and perhaps are widespread across the whole brain? Oftentimes the methods and the assumptions that they use end up defining a field in ways that are very, circular and not direct and not obvious. And I think it's very important for people that work in methods like myself and many others to try to keep those things in mind. Like how is it that the method that you are developing is helping or not in allowing researchers to ask questions, whatever the questions are they had before you provided the methods, not driven by the availability of the methods that you provide, right? So basically allowing researchers to express those ideas and ask the questions to their data in a way that is not biased by the availability of this tool or this other tool or this particular method that will allow you to just look at only that precise aspect of the data. So all of this is a very important thing to keep in mind.
I haven't thought about that too much, but that's very true. The medium is the message in a way. Well, so we've been talking for a while now. Unfortunately, I do need to go pretty soon, but I would like to continue talking about this at some point, maybe a year from now. We touch base again, see where the CONN Toolbox is at, what some new developments are going to be. Because again, it seems like it is more or less, it'll continue to be supported for the foreseeable future. Aside from you, I don't know if there's an heir apparent. I know you're probably not retiring anytime soon, but it does seem that you do the majority of the updates and all of that. But we'll talk about that. If there's anything you want to close with, any closing remarks about the CONN Toolbox, where it's at, where it's going, anything else that you'd like to say?
No, thank you very much for having me. I think this is great. I'm totally up for meeting again next year and kind of revisiting the status of the field and of the CONN Toolbox. If I want to close with anything, it's just again I want to repeat how much I appreciate you having me here and how much I appreciate your work. Particularly, I think is great. All of the resources that you put out there for people, educational resources, your book, your videos, your everything. I really appreciate it. So thank you very much, and it was an honor to be here and a pleasure.
Great. Well, Alfonso, thanks again. Hope to see you soon. Keep up the great work. We'll put those links about the CONN Workshop and any other resources we think that the viewers might profit from. So thank you again for your time. And
thank you very much.
Of course. We'll see you soon.
Let me know. I'll talk to you soon.
All right. Take care. Goodbye.